some detail about the intermolecular Coulombic decay, and then we will see why it has no bonds. If you consider the electrons in atoms and molecules, they could be classified into core shell, intermediate shell, and outer shell electrons. The core electrons are more tightly bound to the nucleus than the intermediate and outer shell electrons. The energy of the electron increases as we go from the core to the outer level. Today's talk is all about the decay of a single vacancy that is there in any one of these shells. A vacancy in core, intermediate, or outer shell. So the talk is all about decay of a single vacancy in these three kinds of shells. First, let us see the decay of an outer shell vacancy. You can shine a photon and excite an outer shell electron to a Rydberg level, which are high-lying levels in the atom, and thereby you can create the outer shell vacancy. This outer shell vacancy is unstable. It will decay in the sense that the electron from the Rydberg level will fall down and fill the vacancy. The difference in the energy between the Rydberg and the outer level will be the excess energy in the system, which will be radiated as a photon. So, you see, the outer shell vacancy decayed by radiating a photon. So, we call this as a radiative decay. The typical lifetimes are in nanoseconds for the radiative decay, and the actual lifetime will depend whether the atom is free or is a part of a molecule. Next, let us see a decay of a core shell vacancy. Core electrons are more tightly bound, so we need to spend more energy to remove the core shell electron by X-ray, say, and thereby creating a core shell vacancy. Now, this core shell vacancy is unstable. It will decay in the sense that an electron from the outer shell will fill the vacancy. Now, the difference in energy between the outer shell and the core shell is the excess energy in the system. It needs to be released, and it could be released as a photon. However, in many cases, this excess energy is sufficient to kick another electron from the system. We call it as a OJ decay. Okay. So, you see, the core shell vacancy, a single core shell vacancy, decayed into two outer shell vacancies without radiating a photon. And this is called OJ decay. The lifetimes are in sub-femtoseconds for this kind of decay, so it's faster than radiative decay. So it will outpace radiative decay. Okay. Now, so what we are, and the core shell decay, vacancy decay, the lifetime of the core shell vacancy is hardly influenced by the environment. So we saw that outer shell vacancy decays via radiative decay process, and the core shell vacancies decay by OJ emission. We call this process a OJ process. The next thing that we need to see is a decay of an intermediate shell vacancy.
Aravind, just small query. This Redford level and
levels of the atom. It's still known they are very close to the ionization continuum. Yeah. So, the next is to see a decay of the intermediate shell. Let us take a look at it with a very concrete example. This is the neon atom. In the neon atom, the energy ionization potential IP to remove a 2s electron is about 48 dBs, and the same for creating a 2p hole is 22 dB. So let us send in a photon and kick a 2s electron out, thereby creating a 2s vacancy. This 2s vacancy state is 26.84 eV above the 2p vacancy state. So it will decay down to a lower state, below 2p hole state, which means the 2s hole, the 2s vacancy will decay to a 2p vacancy. The excess energy of 26.84 eV is available in the system. And one might think that with this energy, we could kick another second electron, 2p electron from the system. However,
What do you mean? It is available in the system. There is a photon emitted, right?
no. So what happens is, I have already created this 2s vacancy.
Right.
Now this 2s vacancy is above 2p vacancy. Now the 2s vacancy could decay to this 2p vacancy. Now I have this. Now the energy could be, as you say, could be radiated as. I do not know whether it's going to be emitted radiatively or I'm just arguing on that, debating on that. So the excess energy is available, but one could think that just like the OJ emission, maybe this energy could kick the second electron.
The excess energies are certainly not available with the atom, right? You are talking about a collection of atoms.
Yes, it is the system, right? So you make it is like it is simple. I am making a transition from one level to another level, and the energy has to be released now.
Correct.
Now this excess energy, could be used to kick an electron, like the OJ process. Okay, that is the idea. However,
What about angular momentum?
what is that? I didn't get you.
2p as non-zero angular momentum,
Correct.
2s as 0.
Yes.
Just to get energy, it may not be enough.
Selection rules.
Yeah.
But this is dipole about.
This is dipole allowed. 2p to 2s
Just
is
let it go up as a photon.
it is. Just give me a moment. It's going to go as a photon. So what happens is, one might think this excess energy could kick another electron from the system. However, the energy for ejecting a 2p electron from the neon cation is greater than this 26.84 eV. Okay? In fact, the lowest double ionization potential for the neon, that is the lowest double ionization potential in the sense that the lowest energy, the least energy that you need to remove 2 electrons from neon is 62 eV, which is above the 2s vacancy state. Therefore, the 2s vacancy state cannot become a 2-hole state.
It's because of the positive charge 2p electron is deeply bound.
Yeah. Okay. So what happens is, because of this, unfortunately, the doubly ionized state in Ne2 plus is energetically forbidden in this case, and the excess energy needs to be emitted as a photon. And the lifetime is about 0.2 nanoseconds in this case. So, you see here, I need 22 eV to remove a 2p electron from neon atom. However, 26.84 eV is not sufficient to remove a 2p electron from the neon cation. This is not surprising because in a cation the electrons are more tightly bound. Okay? Or in other words, when you have the two holes in the neon system, the strong Coulomb repulsion between the two holes in the neon makes it a very high, energetically a very high state for access. Okay. So, if the blockage for the electronic decay was the presence of two holes in one single site, then we should expect something interesting when you go for a dimer. Okay. In the case of, I'm going to consider neon dimer, it's a van der Waals dimer, and the separation between them is about 3.4 angstroms, a very weakly bound, this 2 millielectron volt is the binding energy for this van der Waals dimer cluster. And you see that even in the dimer, the ionization potential for creating a 2s hole and the 2p holes are the same as the case of the monomer. Also, the double ionization potential to create two holes on the same unit of the neon dimer is also roughly the same as the monomer. However, now we have a scope to have these two holes separated and located one in each side. Okay, thereby reducing the reducing Coulomb repulsion. Therefore, what happens is the two-hole ionization potential drastically falls down. So much so that it falls down below the initial 2s vacancy in the 1 molecule. Okay, so which means that I can now, if I create a 2s hole vacancy in one of the unit, which is this state could decay to a state which has two holes, one in each the neon unit. which means a 2s hole, 2p electron will fill this vacancy, and there is an energy transfer, which is via dipole-dipole interaction. It's a virtual photon, and the energy transfer kicks a 2p electron from the neighbor, resulting in two holes, two-side two-hole state. Now you see, an electron emission pathway which was blocked initially is now open. It makes a lot of difference. Why? Because electron decay is much faster than the radiative decay. Radiative decays are in nanoseconds and electron decays are in femtoseconds, which means that this kind of emission will outpace the radiative. Okay. Now you see that the initial 2s vacancy decays and kicks an electron from the neighbor. And this energy transfer was simply due to the Coulombic interaction between two atoms. So the decay is due to the Coulombic interaction between two atoms. Therefore, it is called interatomic Coulombic decay. So in interatomic Coulombic decay, an excitation decays and ionizes the neighbor. Okay. Now you form two neon cations. They cannot hold together, they will fly apart because of the Coulombic repulsion. Yeah.
So, this is Srilanka versus back. So, in the beginning, so when we are trying out one molecule,
From the 2s.
we have provide some energy.
Yes. Yes.
That energy the beginning we have provide, then all these processes will happen.
Exactly. When I discuss the experiment in detail, the energetics will come. First, I need to give a sufficient energy photon to kick to create the 2s vacancy. Right. So now I have these two neon cations that are formed. They cannot be together. They will fly apart. So this is what is called the interatomic Coulombic decay, and the lifetime is 60 femtoseconds, 1,000 times faster than the radiative decay. So it will outpace the radiative decay. So this channel will operate in the cluster rather than the radiative decay. You see the difference? So
This could happen in liquid also.
yes,
It's a dimer.
yes, people have measured it in liquid water.
Aravind, can you give some insight as to why this is so? I mean, why is this much faster?
Yes. The OJ decay, the electron dynamics is usually in very fast than the radiative decay. With the electron, because this kind of thing is all about the Coulombic interaction between the electrons, and the electron dynamics is much faster than the radiative process. So if you measure the width for the Coulomb, the decay width for this, they are much larger because the electron dynamics are much faster than the radiative. Okay, so it actually ICD bits are are comparable with local OJ bits. Sometimes they are even larger than the local bits.
So the matrix elements that come here are Coulomb matrix elements.
Exactly.
Whereas in the previous one, they are dipole matrix.
Exactly. So if this is going to happen between two atoms, the same could happen between molecules. In fact, Professor Sedabon first predicted this in the HF molecular dimer, where the same process occurs. You can see the 2s vacancy in the monomer is above the double ionization potential. On the other hand, the dimer, the 2s vacancy is above two-side two-hole vacancies state. So naturally, this intermolecular Coulombic decay will occur. Now, whatever we discussed is called direct IC. So you created a hole and the hole was filled, and this energy was transferred to the neighbor and kicked in it. You can also have something different slightly. This hole could be filled by a 2p electron from the neighbor. Okay, and the excess energy could kick an electron from this acceptor. This is called exchange ICD. Okay, the initial and final states for these two are the same. However, for certain reasons, exchange ICD is weaker than the direct ICD. Okay, so direct ICD is what you see. The initial and final states are same for both. Now, since we talked about exchange ICD, it is tempting to have a small digression. Let us consider a mixed dimer, neon argon dimer. We have created a 2s hole to begin with a photon, and you see that the state that corresponds to single neon hole argon is above neon neutral with two argon groups, which means this particular state could decay to this neon argon 2 hole state, which means that this neon has to be neutralized and then we should have a dication on the argon. This could happen by exchange of an electron from argon to this to make this neutral, and the energy is used to pick another electron. This is called electron transfer mediator decay. This is also observed in many systems.
But these interatomic transfers are probabilistic.
Yeah, no, I didn't understand this.
I mean, why the interatomic energy transfer is probabilistic or one?
It is one of the two possibilities. The other one is the radiative process, and the second one is this. So there is a competition where this one wins. Now, if you have, we talked about neighbor. There was a neighbor which can take with which you can share the energy. Now, if you have many neighbors, the ICD rates, ICD channels increase, and then the ICD rates keep growing. A nice example for this is endohedral fullerene. You have a neon atom, for example, caged inside fullerene. Okay. Now, inner vacancy in the atom could be filled by an outer shell vacancy. The excess energy could kick an electron for the cage. Okay. So there are many possibilities now. It could happen. There are many channels for from which the electron could come out. So the calculated ICD rates are exceedingly high for this particular system because there are many channels. So everything is fine. Do we have an experimental evidence for this ICD? The first experimental evidence for ICD came from a very nice experiment, simple, beautiful experiment. You see, how do we measure ICD? I have a dimer and I use a photon of energy, very wisely chosen energy, that is energy which is lying between one side and two side ionization, which is 59 eV. Now with this 59 eV, I will create a 2s hole in the one of the side, and the photoelectron that goes out will take about 10 eV energy, right? Because 59 eV, and I'm going to this state, which will finally decay to 2 hole state. When we form this, when ICD occurs, when I form two neon cations, they're going to fly apart into two neon cations. Okay, dimer will fly apart as two neon cations. However, when I do this experiment, I will not only have my neon dimer, but I also have monomers in the system. The gas beam monomer population will be more than the dimer. Even the monomer will get ionized by 59 eV photon, and you will get neon cation from the monomer as well. However, the neon cation that comes from the monomer will proceed with the same gas, neutral gas velocity, which is very slow. On the other hand, the neon cation, that is, the cations that are formed from the ICD process, will, because of the Coulomb repulsion, they will split apart, they will move with a larger kinetic energy and also with equal and opposite momentum. Okay, so you can simply wipe off the background. This is the beauty in this experiment. So you can completely remove the background and look for those events wherein you get two neon cations which move with equal and opposite momentum. How do you do this? So this observation of two neon cations flying apart is going to be an unequivocal signature for this ICD. This was done by a group in Frankfurt here. So what you do is you have position sensitive detector and you have an electric field which will drive the cations that are formed. Imagine that the bond axis at the time of ICD is oriented in this direction. The two cations that are formed, they will fly apart and this electric field will take them to the detector. Depending on the orientation of the bond axis, one of them will arrive before the other. We call that as time of flight as the first hit and time of flight as the second hit. By measuring the time of arrival, we get the speed of these ions. By recording the positions of these particles and the speed, we get the total momentum. So at the end, after collecting the entire data, I can look for those events that had two guys that were traveling apart in equal and opposite direction. Okay. So, and the electrons will, you can also do electron measurement because the electric field, electrons will move in the other direction. This experiment is set up as called cold trims, and Shiva is here, he's an expert in cold trims. Yeah. So now, so what you do is, if you know the energy with which these two neon, if you know the kinetic energy that is released during this explosion, Coulomb explosion, then for every orientation of the molecule, you can actually simulate the times of flight of the two ions that go and hit the detector. Okay, and this is a simulation for the times of flight for the time for the first ion versus the time of flight of the second ion. This is the line that you expect for neon dimer. Both of them are the same, and the other one is isotope substituted, and you have isotope also in the population. So you got two lines to this, and the experiment produces. So you see, this is the beauty of this experiment. You can keep reading this paper a few times. It's such a nicely written PR paper.
In the orientation of the dimer is random.
Yeah, random, and hence that is why you get this line. So for every orientation, you have a simulation. Fantastic experiment. So now, how do I get the energy released during this experiment? It's very simple. You see here, the initial 2s whole state is decaying into two 2p whole states. Therefore, the energy released is simply 48.48 eV, which is this energy of this 2s whole state, times minus 2 times this 2p whole state, which is 5.16. This 5.16 eV should be shared between the ICD electron and the two nucleons, two positive cations. That is what they have. So, if you remember, I mentioned that the photoelectrons will go out at 10 eV, about 10 eV. You can see that. And the sum of kinetic energy of the ICD electron, the two neon cation, is 5.16 eV. So, when you plot the total kinetic energy of the cation versus the ICD electron kinetic energy, it should be a straight line, as you see here. Okay? And you see that when they will add up to 5.16, when KER is, for example, when KER is about 3 and this guy is about 2, they will add up to 5.16. They correspond to one single event. So this actually put it in a very firm foot in this ICD process, this particular experiment. Now, a different kind of it, which Shiva is very, has done several experiments on this. Yes.
How do you know on the detector side, how do you know the effect? Because you have multiple events.
Yeah, so what we do is a very important question. So the events are, we do it in the collection efficiency is brought down. We don't have if you have two events, then you have false coincidence. So we keep it down so that, it's a procedure that. Another very interesting ICD is when you consider a helium dimer. Now we are not going to ionize anything, but we are just going to create a vacancy in the ground state by having a transition between 1s2 to 1s2p. That is, I send in photons and excite to both the units of the helium dimer to the 2p level. Okay? Now, one of them will fall down back and give the energy to the other, and the electron will be kicked. So we have a helium dimer, both are excited homebound transition. Okay. And then one will de-excite, the energy is transferred in. And these experiments have been done in helium nano droplets. So you send in high intensity lasers because there is a problem here. When you have a dimer, both have to absorb photons. The dimers are very close, both units of the dimer are very close by. So you need to have a large number of photons in a small region. So you need high density photons in this case. This is a drawback in this setup in the sense that the natural environments, it's not very likely.
So these are two photons. One photon here, another photon.
Yes, one photon here. They would have to. Before the lifetime is over, they have to have that. So now when you send in this, some of them will get excited and some will get de-excited, and the Coulomb explosion will happen from the nano droplet. The excited, the helium cations will fly away. Those which receive the energy will get the repulsion, because of the repulsion they will fly away. This is for collective ICD because, unlike the previous case, both the units participated in the energy absorption, both were excited. So collectively there is an ICD that is happening. And there are nice experiments on these collective ICTs. So you can actually classify the ICTs that have been done till now in these two categories. One in which an intermediate excitation in one of the unit de-excited and the ionized the neighbor. The other, it both got excited and the collective ionization that we just discussed. The former, since we are actually removing electron from an intermediation, the expenditure is larger than we need to have extreme ultraviolet photons. On the other hand, in the second case, as we just saw, we need high intense lasers. So FEL lasers, free electron lasers are used to perceive this ICT. Now, so both work only in clusters, bound systems, and they have their own disadvantage. One is requiring high photon. You can also achieve this excitation by particle collisions as well. That is also done. And both work in bound systems. In our recent experiment with pyridine monomers, we realized that ICD need not occur only in bound systems. It could manage even to occur even in unbound systems with our experiments in pyridine. We prepare pyridine vapors and let it into the interaction chamber through a pulse form. So we do not mix it with any carrier gas, and there is no supersonic expansion in the sense that you can produce clusters. So we have essentially pyridine monomers that are going into the interaction chamber. Then we shine 266 nanometer photons on pyridine monomers, which is having mass 79 AMU. And once you send the pulse laser, we apply a high positive potential on this repeller so that we can sweep any cations that are formed towards the detector. I start the clock when I apply this repelling voltage, and I stop the clock whenever a particle hits the detector. So I have a time of flight for every particle that hits the detector. And since all these masses positive, they are singly charged mostly. Depending on their mass, different masses will arrive at different times. So from the time of flight spectra, I could get the mass spectrum. So this is what was recorded with 266 nanometer.
So are we safe for all the particles?
Yes. So initial time they arrive, the bunch arrives, pulse to bunch arrives in this interaction region. Then I apply the laser, pulse laser on the interaction region when exactly the pulses at the interaction region. So all of them get excited. The laser pulse is 6 nanoseconds per time width. So they all start to.
So T0 is same for all the
T0 is same for all the layers. And T0 is the time at which I apply the repelling. They go. Normally they will not go as cluster. When you have a monomer, they are supposed to go as a monomer cations or fragments of monomer. That is what. So what I mentioned was I let in this gas, pyridine monomers. Then I have a 266 nanometer light. I do not know what will happen with 266 nanometer. What I mentioned was if suppose cations are formed, then they will be swept towards the detector. We have to see how whether cations will be formed at all. In our spectra, we observe the formation of these pyridine cations. You can see that I see a cation at the 79 AMU mass, which corresponds to the pyridine parent cation. Yes, it is biased so that it can take the positive ions. Now, there are several questions that we need to answer in this to understand this spectra. The first and the foremost is that how am I forming these cations first of all? The reason is the single photon energy. I am sending in 266 nanometer laser photons. Energy of every single photon is 4.66 eV. And the ionization potential of pyridine is 9.24 eV. So how is it possible that these pyridine monomers are observing photons and getting ionized? So this is a question that we need to answer. Maybe one could argue that it is via a 2-photon absorption process. But the things are very much against this 2-photon absorption because the intensities that we use are very low, 10 power 4 to 10 power 6 watts per centimeter square. Typically, multi-photon absorption do not happen at such low intensities. Okay. So still,
what is the gradient concentration?
So what we have is about 10 power 15 per centimeter cube. Every pulses.
Which would be enough for
No. Because what is required for a 2-photon absorption is that consider it doesn't depend on the density of the guy who is absorbing the photon. If I have a molecule, I should have 2 photons roughly within the time of the light. I absorb 1 photon, before I decay, I need to take the other photon. It should be 2 photon, so you need to have a high density of photons for that to have. Typically, they are about 10 power 7 watts or 10 power 8 watts is the intensity level. Still, never mind. Let us assume that we have a multi-photon absorption. If you have multi-photon absorption, then the maximum kinetic energy of the electrons that come out of the periodic cation will be 2 times the photons energy minus the ionization potential, which is 80 millielectron. And we record electron kinetic energies that exceeds even 500 millielectron. So where is the energy coming from? This is very important to address. Another most important point is the following. When I have a multi-photon ionization, the electrons that are ejected are not ejected isotropically with respect to the laser polarization vector. Typically, there is an angular distribution about the laser polarization vector, which is having the signature, which will have the signature of the orbital from which the electrons move. Okay, so you expect an angular distribution for these ejected electrons. But we took an image of these electrons using a velocity mapping imaging spectrometer. We observe this is the laser polarization vector, and we observe isotropic emission of these electrons. It clearly rules out any kind of photo emission that is happening. So the isotropic emission of electrons and also the energy that you see for the electrons, they rule out the NP in this case. Now, I don't know how I am producing the ions, that is fine, but there is another question that we need to answer. I know for sure that I am getting in periodic monomers into the system. Then how do I get these ions which have mass larger than the parent? I have a mass at 106 AU whose yield has been divided by 10 so that it could be displayed neatly. And you see that it is much larger than the monomer yield. And I also have a mass greater than the dimer mass of the period, 2 times something else, which is greater than that. I have still dehydrogenated prime. Now, how do I form these ions when I don't have any cluster to take? In fact, we wanted to test whether we wanted to make sure something is odd here. So we built an electron gun and we studied the electron impact ionization and the same experimental condition. We just remove photons, we put electrons. And now in this case, we do not see any mass above the parent. We see 79, these are the energies of the electron energies and they impact on the periodic molecules. We don't see any molecule ions that are beyond this parent mass. And we see this mass which is very well known, HCM loss from molecules of this kind. So this is what we observe. So there is something very peculiar when you have photons. And this also asserts that we do not have clusters to be. So now, what is that? And third question that we need to answer. Yes.
So you have identified that
Yes.
So what about the other states that you get?
These guys are fragments that come from parent. Okay, I'm going to talk about how they are going to form also. Because I have not completed the fragments, all these fragments need to be discussed. Okay, they are actually fragments that are formed. At the moment, we can consider that they are the fragments that are formed from the parent mass. Whenever you ionize someone, there is also some excess energy that you dumped in. The electron takes some energy and some amount of energy remains in the nucleus. And that goes to the nuclear modes and we have fragmentation. So, you always expect.
But it's subtraction, the ionization energy is very high.
Yes.
So then you don't expect that much fragmentation.
Exactly. And that would again at low intensity. So, yes.
How do you rule out the presence of clusters?
Yeah, if you had clusters, first of all, we just merely open the pulse wall and we behind the pulse wall, the vapor pressure is within this what is the pressure. And you have high pressure, high vacuum in the interaction chain. Typically, when you want to make clusters, you mix it with, you dilute the system, pyridine or whatever with gas and pulse it via a nozzle. So there is many body collision happen at the nozzle, and there is a cooling that happens and you produce clusters. You cannot simply produce clusters just by in the low pressure, you need high pressures. And moreover, if there were clusters, you see the heavier than parent cations are much larger in intensity than the parent cation. So you could see them even in the electron impact ionization aspect. We don't see any of them, even as gentle when you come to the electron as gentle as 20, 12, we don't get these cations. Okay, so that eliminates the cluster. And there are also other reasons. At the end, I will come back to a question that even if it was cluster, it has to be what we like. So we will discuss that at the end. Yes.
But this will have a tendency for stacking the way this will be.
Yeah, that is going to be the answer. So even if it was a cluster, it has to be what I'll come to that again. So I can even maybe I can even do that now. See, so suppose imagine I had a cluster, the dimer for example. With that, I could explain masses that are between 17 and 18 on the dimer mass. But then both these guys have to absorb 2 photons, one each. Okay, and not at the same intensity. It cannot happen at such low intensity. So it needs because they're going to be very close. I need large number of photons in that small region, which is possible at high intensities. Right? We see this process even at 10 power 4 parts per second. It's not possible. Yeah, and even if they are clustering, they are supposed to be their population is supposed to be much smaller than the mono. But we see the other way around.
A related question: even if your photon intensity is low, there will be a probability that 2 photons are locally present at it's like a Poisson distribution where small probability you can have having 2 photons at the same place.
Fine, there is no problem. Even if that happens, you cannot have the greater than parent cation is more than the parent cation. That is the issue. So, it is because it is going to be stable. Excitement is normal and then it's going to be coming down and emitting the radiation. This is just stable. So now, most important question, the third question is more important because the referee asked that. So how do you form ions here whose appearance energy is greater than 20 eV? Appearance energy means you give me pyridine monomer. I need to dump in 20 eV to create finally whatever EV process. I need to dump in 20 eV to get some ion. That is appearance energy for the ion. There are some ions that are absorbed whose appearance energy is about 20 eV. Your photon energy is just 4.6 eV. So there is some issue there. You need to address all these questions here. So now, what is really happening? What is the difference between the photon? What happens really with photon, which is not happening in an electron experiment, is that I have at 266 nanometers, I have a resonant transition, bound transition pyridine monomers from that is pi star excitation. That is a bound transition between from the pyridine on the exciter. Pyridine monomers are excited. Now, if we need to now account for these heavier masses, so probably there is in the excited states the molecules are undergoing some interaction. Okay. So that is actually in many fields it's called cycloaddition, chemists call them. It's all possible when you are in ground state the molecule may not be interacting, but in the excited state they may be more interacting. These molecules are pi molecules, as Manu said, they already have tendency to come closer. And they have this pi stacking. But then now in the excited state, probably these interactions are amplified, then they can come closer. Okay. So what we did was we calculated the energy, the association energy between two excited monomers. We did for both the ground state monomers and the excited monomers. And we see that when you consider two cofacially approaching pyridine molecules, In their ground state, they do not form any association. What you have in the x-axis will be intermolecular distance, and what you have in the y-axis is the association energy. So you see here that in the ground state they are not associating much, but in the excited state, at these intermolecular distance, they have heavy association. Okay? They tend to form bond-forming association. So you can see that if the association energy is positive, then its association is preferred, and the energy released during the association is as high as 7.5 eV. Okay? Now, so in the excited states, they are coming together. You can also see that you can compute these are the three pyridine molecules, and their wave functions. You can see them; they're overlapping. They're forming a bond-forming overlap. The wave functions are forming bond-forming overlap. So covalent associative interactions is very strong in their excited state. So what really happens is, so what happens in the excited molecules, pyridine monomers, they are associated. So what happens when two monomers, excited monomers are associated to form a dimer? The total energy in the system is barely above the ionization potential, because 4.66 plus 4.66 is 80 millielectron volt above the ionization potential. And we do not expect this combination to undergo IC, right? Corrective ICT, that one will drop and the other one will keep the electron, because the excess energy is only 80 millielectron volt, and then there's a large molecule. There will be some channeling of energy from the electronic mode to a small fraction is always expected to be channeled from the electronic mode to the nuclear modes of vibration, called intra-vibration energy redistribution. So 80 millielectron volt, we do not expect that it could ionize. However, when it associates with another exciter monomer, then two of them can de-excite, and the energy could be shared to the third monomer, excited monomer, and it could keep the electron isolated. So it is like collective ICT. To begin with, you see the advantage here. To begin with, the molecules are not bound, which is favorable for us because you don't need high intensity laser to begin with, because molecules are very far apart. So you excite them, and then they form this association. En route to the association, ICD happens. Before the full association happens, en route to the association, ICD happens. Then two of these guys de-excite and exchange the energy with the third excited monomer, and then ICD electron is kicked, which is supposed to be slow and isotropic as we measure. So, and now you see the following. Even this should answer Ranjit. Even for the formation of from what we see here, even for the formation of the parent cation, I need three guys to come together, three excited guys to come together. So which means 3 photons should be involved in this picture. So if I plot the ln of the ion yield versus the ln of the laser intensity, it should be 3, and that is what we observe. You cannot expect slope of 3 at such low intensity lasers. Okay, it is not possible. No, it doesn't happen to the ground state. Only after it excites. So the rate determining step is the association of 3 excited monomers, and that is why you get a slope of 3. Exactly. But the excitement finally, it will drop down and then go here. Since it's bond forming, finally I get all this cation of the so dimer and larger than dimer.
So now ions have new covalent bonds.
Exactly. Yeah.
Now go back one slide back.
Yes. Yes. Yes, exactly. This guy will give you that information, that you have a wave function overlap. The red color one and the green color ones, they represent the two phases of the wave function. Nice overlap across the green. Yeah. That is something that it has to stay around. Yeah, so in this case, pyridine, and we observe this process in few other molecules. They belong to this pi molecule. So what happens is you go from S0 state to S1 state, and this S1 electronic state is degenerate with higher vibration states of S0. So they keep going back and forth. Once you are in a higher vibration state, vibrational lifespans are microseconds, so you are safe. So you keep going back and forth. This is one possibility. The other possibility is probably there's a triplet state to which it's going and then it is there. So, which makes sense, and we don't observe these things in, say for example, water molecule. Water absorbs 260, it's fantastic. There's a nice absorption of 260 at 260 nanometer. We don't see such thing happening.
Sorry, I have a short.
Yes.
Suppose you add an electron and make this primer neutral.
Okay.
Is it stable?
The primer itself will not is not stable actually.
In the long term, it has an ion.
Yes.
Suppose you add
Not just because of ions. What happens is that as they associate, there is an association energy that is also released. 7 eV of association energy is released. So it breaks the molecule. That's why we get all these fragments from parent. Yeah, all these fragments come from the association. That's why we can answer the 20 eV appearance energy from ions. So 3 photons is opposed to 13 eV, 13.4 eV. Then the other one is from the association.
So new fragments may not look like part of 3D metal.
No, not at all. Maybe even in fact that's a good point. The fragments that we get below the lower mass, they do not even resemble those. We don't get those fragments in electron impact ionization of molecule. So you get a different. So because of the association. So then, so this is a very important result that the slope is 3, and this is the 3 for ICT that, and finally. This primer cation is not stable because the excess energy in the system, it will fragment into all these fragments that we absorb, the parent and less than parent and up to dehydrated primer. We do not see the primer, that is very important. The primer cation is not absorbed. We see a dehydrated primer because the excess energy, at least the H bond has to go out. And the yield is also very small. And so the association energy accounts for the appearance potential. So, if you just consider all the enormous amount of literature that is there on ICD, fantastic experiments are there. There is a bibliography that is maintained on ICD. There are 400 papers, both in theory and experiments, are there. And this particular review summarizes all the existing work on this. And there you find this kind of chart where they actually summarize all different kinds of ICD processes. For example, the systems that are studied could be classified as clusters and also liquid. Very recently this year, they absorbed ICD in liquid water. So then, so you have, these are the systems that are studied. The excitation mechanism that they use are synchrotron radiations, high energy particle beams, and also free electron lasers, because free electron laser can give you high intense photons for this conductive ionization. Then the probes are electron spectroscopy. They look at the ICD electron, they also look at the ions that are formed, the particle coincidence that we just now saw in the neon diver case. You measure the electron and the neon in coincidence. Then you also have fluorescence spectroscopy. These are the techniques that being used. So this is the chart that summarizes the result. Now we have ICD happening in organic molecules that are unknown to begin with. Most importantly, it could happen at ambient intensity because to begin with they are not known. So we can actually do it with ambient intensity and UV photons. And we also use the electron ion spectrum. So this is where we start the movement, and there's a lot of work that are in ICD. Shiva has 3 very interesting work on ICD, experiments on ICD, on nano droplets. You can actually go and have a look.
Then the probability of forming these primers should go down, and then such signals should not show up.
True. It should go down, and they will not form. If at all any ion is formed, you will always see the primer.
So any concentration dependence study was done.
No, what I am saying is, if at all any ion is formed, as per this mechanism, primer has to be formed to begin with.
Right.
Primer cation has to be formed. And if you have a higher concentration, more of it, the primer cation is unstable, it's going to fragment into smaller ones. higher the concentration, it will build more. You can see that even now, primary calculate is not much. But when you go down on the density, yes, it will go down. We have observed even we can do not with just the laser. You can also bring down the laser intensity and observe that display.
So is there any kind of threshold that below this we don't see any signals of this type? But
yeah, I mean, okay. So the least that we have done is the vapor pressure of the brittle. Okay. We could actually go down by pumping the line to go down the vapor pressure. I mean, so we observed even at 10 millibar, 20 millibar is the vapor pressure. We have seen up to 10 millibar, and at 20 millibar, we have seen these ions even at 10 power 4 mass.
thank you.
Yes.
There are at least sort of three structures. The first peak and then shoulder 1 and shoulder 2.
No,
Are they due to some physical process?
No, I don't think we can read too much from that, because this particular stuff is from the Abelin version of the image. Okay, the raw image is in Abelin version, and the spine structures, I'm not very sure that they are really something of any vibrational states of pyridine or no. I don't think so.
Yeah, it was actually what also catches attention is the last piece between 0.5 and 1 EV, which seems to be maybe another process or something. I don't know. Just speculating.
Yeah, this is where this coincidence could help maybe. And with these electrons of those particular energies and then see what happens. I'm sure I need to think a little bit.
Yes. Also because there were some reports, though not on the ICD, but some kind of whether the electrons come out from thermionic process or not in such an aggregate. So maybe that's a question to also
So from the
ask.
aggregate, then this is not a
Since energy collects and some photo emission takes place, there was a Fitzgerald letter where C60 was examined. Where they claimed it's thermionic, so I'm wondering whether we can attribute an emission mechanism
for the
also for these electrons. Yes, sir.
Short.
Yeah.
So what is special about 3D? Benzene.
Yeah, benzene also you could
Get
see.
one NH by
Yeah.
carbon.
Yes.
So will it happen?
Yes, sir. We actually observed this in some few other molecules, not in benzene, because the 5 paisa in benzene is actually very short wavelength, which we do not have.
Why is it? Because
That is right. Yeah. But we have done this in other similar molecules like phenol, and we have seen the same. In fact, we first saw it phenol and decay. So it's about pi star transitions. So there are 5 molecules where the interactions are active.
So in slope 3,
Yeah.
simply in our
Sorry, the slope 3, sorry, Siva, the slope 3 maybe we might have discussed in terms of the thermionic emission.
generally in the luminescence experiments, the lasers we work, the slope 3 is a direct evidence of 3 photon process.
Correct.
But here you are plotting that and getting a nice slope. That's experimental or something?
Experimental.
Yeah. So, and that you are attributing to the event after the excitation, right? After the ionization.
Yeah, I mean the rate determining step is 3 guys coming together. So,
Yes, it's interesting.
the rate determining step is 3 excited, 4 excited stuff coming together.
Yeah, but by the time the laser came and went,
Yes.
so the event has taken place.
Yeah.
But how do you then relate?
Yes, exactly. So even in the ICD process, the connective ICD that we discussed, you have both the helium units of the dimer excited. Even then, after absorption, the Coulomb interaction happens, exchange of energy is happening between the 2 units. So you get a slope of 1 even there, although there are 2. But here, it is not a cluster to begin with. If they have excited, 3 excited molecules have to come together. The rate determining step is the association of 3 photoexcited molecules. So although the ICD is like a single photon process, here one has to form that they have to come closer for ICD to happen. So that is why you get a 3 photon
So it's determined by the kinetic theory of gases.
Exactly.
So
Exactly.
yes.
Yes. There's a fluctuation and there is. So like we have 10 power 15 excited molecules and we record about 100 of these events. No, it's a recorded image of electrons. So no, there is something called delay and anode. So you can actually get the positions of where the electrons hit. It's a very simple idea. So if you have a wire, straight wire like this, and if an electron hits, you apply voltage on this wire. When the electron hits a detector, the detector amplifies the electron flow. And one for every hit, you get 10 power 6 electron flow, which falls onto this wire. Say, let us say I have a wire. Then, when it falls here, the signal will travel to both ends of this wire. So, if it falls in the middle of this wire, then both the signals at the two ends arrive at the same time. Okay, from the time difference of arrival, I can actually get where it hits. So if it is at this end, this signal will arrive first than this. So this is called delay and anode. So you have for x-axis, you have a winding of wire, and for y-axis, you have another winding. So you get both your x and y information. So you can actually get multi-hit. It is in one plane. The neon there is a vacancy that is created in neon. And that it's a 2 years old vacancy. And this 2 years old vacancy is filled by an outer shell electron in the neon itself. And this energy is coupled to the cage. And an electron from the cage goes. And people have done this measurements. Not in, I don't know whether they have done in neon, but some complex in the polonium complex inside C80, they have done this.
I think you showed a layout of the detector in one of the slides. Where you were showing how you measure the pulsar.
Yes.
But the question is, and also you mentioned that you don't use any gaseous medium, right? Do you use any gaseous medium?
No.
Because you mentioned that you are measuring the time of flight. In
Yes.
order to do that, you need the path length.
Correct, we know the path.
In order to know the path length, you need to track it.
No.
How do you know the path? It can go like here, it can go like straight.
True. So that is true. So in this case, it is much more favorable situation. Unlike other cases, you have the molecules are coming in, the gas molecules are coming in, and I'm having a photon beam which is about 2 millimeter. The interaction volume is determined for all of them. So where both the neutral gas and photon interact, there is the interaction volume. Ions are formed there. And I have the voltage to pulse kick them. There are chances, of course, that some of these ions there are two different position times. That is what will determine the resolution. But you have some control to actually bring them, improve those resolutions also by playing the electric field. No, in that we don't take any position resolution. There is no need. We just measure only the time in this experiment. In the other experiment that you tube neon, are you talking about the neon experiment?
Yeah, that you showed a layout of the Prof.
It means cold trips. In cold trips, sorry. What happened? I was thinking
I was asking you, well, I think you remember you mentioned that you don't use any gaseous medium.
Correct.
So then how do you track this path of the particle?
I know the geometry of the apparatus. And I know the electric field that I am applying. The position where these are formed also is fixed by the interaction with the overlap of these neutral beam and the laser beam. So from then I can actually have time of there will be some slight spread, of course, depending on the initial position from which they are coming. Why should we? Because I don't see the problem here.
So it's the tracking, correct? Suppose you have a data. Exactly.
No. It is just different in the high vacuum region, and it's just drifting in a high vacuum tube.
So in a deep chamber, we have multiple layers, right? Each layer will give you a heat.
Here it is not like that.
You can make a firm track.
Yeah, I understand what you're saying. But here it is not like that. It's just drifting through the tube.
So guided random.
Okay.
So it is drifting in one direction because of the electricity.
Yeah, but there's no random.
Yeah, sir, if the random
Okay,
walk
we
is walk is
guide a
there, then
random
there is a
walk.
problem.
By the time it goes there,
Ah.
it may not be a straight line.
It may not be a straight.
By
There will be a slide.
Then that will introduce some bias in the time measurement, correct?
Some
Because the
spread,
length is
yes.
now
Slide
different.
spread will be there.
Some spread is
There will be.
different.
Huh? There's no randomness here, but there will be slight differences. Correct. There will be slight.
That is given to
Width in this. Not in addition to the kinetic energy. Yes.
Astrophysical significance.
Oh, okay. So then I actually I didn't print it all. There are almost like that I forgot. Basically these quinolin and the isodiscrete pyridine, they are supposed to be, they are found in this meteoroid that they have Murchison meteoroid of Bangladesh. They have observed these large molecules of quinolin and pyridine. So when these molecules are ejected from the circumstellar medium into the interstellar, where the density is slightly larger and you have these photons, wide spectrum of photons. So when these molecules are excited, they are coming associating. So starting from the smaller molecule, you can start to build bigger molecules because these 5 molecules are interact. So there's a possibility for them to grow.
Sir, in the neon dimer, when there is a virtual photon, is that process a radiative process or an electronic dimer?
It is an electron.
There's no question. There's one speaker.